Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Gaussian random vectors. This is a topic that can seem a little bit intimidating the first time you come across it, because you look at the formula for the joint PDF of a Gaussian random vector and it looks really complicated. There's inverse matrices. As a student it can be a little bit daunting. However, we will show you in this video that the definition of the joint PDF actually makes a lot of sense once you understand what it tries to capture in terms of the data set that you're trying to model using this joint PDF. We will provide a geometric intuition that hopefully will show you that the joint PDF actually makes a lot of sense. Let's get to it. We're going to talk about Gaussian random vectors, and our ultimate goal is to define a parametric model based on the Gaussian distribution that enables us to model random vectors, so to jointly model multiple random variables. The motivation here to even design a parametric model is the curse of dimensionality. We discussed this more in detail in the discrete case, but it just so happens that when you have a certain number of random variables within a probabilistic model, and that number need not be very large, then the possible values that the random variables can take at the same time explodes exponentially, so that we can't really estimate joint PDFs from data. Again, we explained this in more detail in the discrete case, where we showed that the joint PMF for models that have more than, let's say, 15, 20, or 100 random variables is essentially impossible to estimate due to this phenomenon where the possibilities just explode exponentially. For continuous random variables, it can only be worse, right? Because each of the random variables can have values on a continuous interval or on the real line. So it only gets worse compared to discrete random variables. So in order to jointly model multiple continuous random variables, we need to either enforce independence or conditional independence assumptions, or we need to use a parametric model that depends on a small number of parameters. Today we're going to talk about this second option, and we're going to try to design a model based on the Gaussian distribution. We already talked about the Gaussian distribution in 1D. The motivation for using the Gaussian distribution is that when we have sums of independent quantities, they tend to be Gaussian. We will talk more about this when we define the central limit theorem, where we discuss the central limit theorem. But for now, we just accept that it's a reasonable model for continuous data. And if you remember, the PDF looks like this. It's an exponential of a squared quantity where we have two parameters. The parameter mu, which tells us where this density is centered, and the parameter sigma, which tells us how stretched out the density is. So we're going to take a look at a couple of pictures to refresh our memory. So here the density is centered at 3, and the standard deviation, which tells us how much is stretched, is equal to 1. Here it's centered at -2. We have a larger standard deviation, so you see that the PDF has stretched out. And here it's stretched out even more because the standard deviation is 4 and the mean is 0, so it's centered at 0. So these two parameters, as we saw, we can estimate them using maximum likelihood from data. Perfect. So what's our first idea is going to be to make our life super easy, and we're going to say, okay, we want to model the entries of a random vector that has d entries. How about we just model each entry separately as a Gaussian random variable? We know that Gaussians are good models for at least certain kinds of data, so hopefully this is going to work out. How are we going to actually fit each of the entries? By finding the corresponding mean and the corresponding standard deviation. That would be for the first entry, for the second entry, and so on, using maximum likelihood estimation. All right? What is that joint PDF going to look like? So we're going to obtain a joint parametric PDF for our data, right? We're saying that the entries are all independent and are Gaussian, so the joint PDF is just going to be the product of the individual PDFs. Okay, it's going to be the product. Now we plug in our formula for the Gaussian distribution, and now we realize that we have an exponential here. So when we have a product of many exponentials, we can just add up the exponents. So essentially here we still have, well, we have this product of all of these terms, the product of all of the standard deviations there, and then an exponential of this sum. And this is going to be important in a moment when we look at the contour lines of the parametric model. Okay, but here realize that we obtain a parametric formula for our joint PDF that has the following parameters: mu1 to mu d and sigma 1 to sigma d. Okay, so it's 2D parameters that we can fit from data. We know how to do that. We do it separately for each entry. That gives us a parametric model for our data. Let's try out our parametric model. So here we have a data set of people in the US Army. We know their foot length. We know their foot length and we know their height. Okay, so each of these points corresponds to one person. And now we're going to apply our parametric model. These are the contour lines of the parametric model. So look at the value of the contour lines. Essentially, this is a mountain which is peaking here and then is decaying away. Okay, so it's decaying. So what do you think of this parametric model? Look at it for a moment. Think about it. Well, it's pretty bad, right? Why is it pretty bad? Well, here the contour lines obviously should look something like this. Why? Because taller people have longer feet and shorter people have shorter feet. But we're not seeing this in our parametric model. Our parametric model is oblivious to that structure, and that structure is actually very important. So that's kind of problematic. So now let's try to understand why the contour lines, why the geometry of the joint PDF that we have obtained from our parametric model looks like this. Okay, let's try to understand. In order to do that, we're going to look at the contour surfaces. In the case of 2D, these are going to be contour lines, which are points at which the density, which again, remember, looks like this, is constant. So these are points, you know, like the values of x for which the density is constant. So this part doesn't really matter. The density is going to be constant when this exponent is constant, right? So the points, the set of points for which the density is equal to a constant is just equal to the set of points for which the exponent is equal to a constant. This is, you know, we have to change the constant, but that doesn't really matter. The important thing is this formula here. So now, what is this formula? Let's think about the case where we wouldn't have sigma I. Okay, if this disappears, this is just the formula of a sphere in d dimensions, which is centered at a point where each of the coordinates of the point is mu I, right? mu1, mu2, mu3, mu4. All right, so basically the contour lines in that case are going to be something like that. It's exactly what actually we see here. Why do we see that here? Because the standard deviation of the foot length and the height, they're not the same, but when we account, so here you see that the axes are scaled so that the standard deviation is the same. So this is why this looks like a sphere. If I had actually plotted the x-axis and the horizontal axis and the vertical axis on the same scale, basically this would look like this, right? Because see that this goes from 150 to 2 meters, this goes from 22 to 32 centimeters. So this is how the contour lines would actually have looked like. Okay. So then let's go back to explain that formula. So if the standard deviations are all the same, we get concentric spheres. In the case of 2D, we get concentric circles. And then the PDF is going to be, just to be very clear, is going to decay exponentially as the circles become bigger, but the contour lines are circles. Now, what happens if we allow for standard deviations, where this is the standard deviation in the different coordinates? So essentially, what are we doing by dividing by sigma 1 and sigma 2 in 2D, we're taking those spheres and we're either squashing them or stretching them in the different directions. So this is the formula of an ellipse. You can check that out in Wikipedia, for example. By changing these guys, we can obtain, we go from, let me see how I'm able to draw this. We go from a sphere to an ellipse. But the important, not to an ellipse, depending on the values of sigma 1 and sigma 2. But the important thing to realize here is that because of how the formula is set up, the axes of the ellipse are vertical and horizontal. Okay, so we have an ellipsoid in d dimensions, an ellipse in 2 dimensions with axes that are along the coordinate axis. So here, when we look at our data, we're going to be able to essentially stretch these lines in this direction and this direction. We could obtain something like this. We could obtain something like this. However, this is not going to help us. By just stretching in this direction or in this direction, we're not going to be able to obtain this shape, which is what we want, which is what we actually want. The funny thing is that an ellipse seems exactly the right thing to do for those data. However, it cannot be an ellipse where the axes are aligned with the coordinate axis, because then we cannot adapt to this dependence between the points. So not between the points, the dependence between the foot length and height. So what can we do? Think about it for a moment, maybe. It would be very nice if we could rotate the axis of the ellipse. And that's all it is. Once we allow for rotations of the axis of the ellipse, we're going to obtain the Gaussian random vector parametric mole. That's all it is. As we will see, the formula looks a little bit complicated and so on, but the point is as simple as that. We want to be able to fit data with ellipsoidal contour lines that are rotated with respect to the coordinate axis in order to capture, to some extent, the dependence between the coordinates. So we want to allow for rotations. How do we do that? Well, we have to go back to our formula for the contour surfaces or contour lines in 2D. What we want to do is we want to include this axis of the ellipsoid that are going to be orthogonal, right? This is still going to be an ellipse, it's still going to be an ellipsoid. We're just going to rotate it. We're going to do, if you want, a change of variable, which is going to tell us where, in what coordinate, like how the axis should be rotated with respect to the coordinate axis, so that we get this rotated ellipse. The formula is going to look like this, right? This is the change of variable that we apply. We essentially take the inner product with each of these, with each of these orthonormal vectors that tell us the directions of the axis. These are additional parameters, so we're going to learn them so that we can rotate the ellipse or the ellipsoid in the case of d dimensions in order to adapt to the data. So this seems like a bit of an awkward parametrization where we have these additional d orthonormal vectors. It turns out that we can obtain a much simpler parametrization that is completely equivalent, realizing that we can actually write this formula in matrix form in this way, where we have this matrix U that has the orthonormal vectors as columns. This formula can be expressed as applying U to x minus mu. Remember that, maybe I should have made that a little bit clearer. Mu has as its entries mu1, mu2, mu3, so mu is just where we're centered. So you can actually forget about this for this argument. This is just where we're centered in space. Once we know where we're centered, okay, which is given by the parameter mu, now we want to see how stretched we are in different directions, but also how we want to rotate the ellipsoidal contour lines to adapt to the data. So these formulas are equivalent. We can put all of our orthonormal vectors that tells us where the axes are aligned into this matrix U, and now we need to stretch them, okay, in the direction of that particular axis by this additional parameter, which are the standard deviations or the variances if we take the square in those particular directions. Okay, so this was a little bit complicated, maybe, but the point is that we want contour lines of this form where we have this called a quadratic form, where our centered vector, let me describe it again, hopefully to make it a little bit clearer. Our centered vector is applied to this matrix in the middle. That matrix in the middle, we're going to call it the inverse of a parameter matrix sigma. This parameter matrix sigma is going to be called the covariance matrix parameter of the Gaussian random vector. Later on in the course, we will see that covariance matrices capture the variance in every possible direction. So remember that for a Gaussian random variable, the variance parameter is just the variance of the Gaussian random variable. We will show that when we talk about variances. We haven't talked about that yet. Something very similar is going to happen here. This parameter that we have just defined captures the variance in every possible direction of a d-dimensional space for a random vector. But let's not get ahead of ourselves. What have we done? We have said, okay, we can define this matrix sigma that essentially encodes both the sigma parameters and the orthonormal vectors that tell us how these axes are aligned. And it just so happens that any symmetric matrix can be expressed in this way. That's called the spectral theorem. We will also talk about this later on when we talk about principal component analysis, but let me tell you right now, every symmetric matrix has an eigendecomposition where it will have the eigenvectors that are orthonormal, and the eigenvalues are going to be real. So if all the eigenvalues are non-zero and positive, this is a positive definite symmetric matrix. This is exactly equivalent. The parametrization is exactly equivalent. If I tell you these guys, like the u's and the lambdas, which in our case correspond to the square of the standard deviations, if I tell you those guys, you can build this covariance matrix parameter, but it can also go the other way. If I give you a covariance matrix parameter that is symmetric and positive definite, you can extract the eigenvectors and the variances from it. So this is completely equivalent by the spectral theorem, this parametrization. Essentially, this means that, let me go back for a moment, that this way of writing the contour lines is exactly equivalent to this way. If this covariance matrix parameter allows us to generalize our model and allow for rotations of the contour lines. Now we have to go back and plug in this in to the joint density so that we obtain a valid joint density that has those contour surfaces or contour lines. So we're going to essentially plug it in here. Remember that this is where the contour lines or the contour surfaces come from. With rotation, we obtain this formula. Now here we have to divide by the determinant so that the joint PDF integrates to 1. This is just multivariate calculus. You can either check or look it up or just believe me. So we have obtained this more general parametric model, which has the same parameters as this guy and some additional ones which tell us how to rotate this ellipse, which are implicit within the covariance matrix parameter. And this is what I meant. If you just look at this formula in general, looks very complicated, but you just need to remember that it corresponds to basically what we want to achieve is ellipsoidal contour lines that are decaying exponentially and can adapt to our data by rotating. All right, so this is what we obtain when we fit our new parametric model that allows for rotations to the data, and the result is much, much better. Okay, so in general, we define Gaussian random vectors as random vectors that have this joint PDF, where the parameters are the mean at which the density is centered. Okay, this contains these mu1, mu2, mu3 parameters, and a covariance matrix parameter sigma that essentially tells us how the data are stretched in each direction. In particular, this joint density again is going to have ellipsoidal contour lines. The covariance matrix parameter tells us how these contour lines are rotated and what stretch do we have in every direction. Because of that, this parameter needs to be symmetric and positive definite. It has to have positive eigenvalues. Let's take a look at an example. Just to show you that the parameterization is equivalent, you don't need to give me the axes of the ellipse. They're going to be implicit in the covariance matrix. Let's imagine that we have a Gaussian density that is centered at the origin and has this covariance matrix. So in order to find the contour lines, the density looks like that. The contour lines, by the way, since we're here, would look like this. Okay, so you're on the mountain and you're in points where things are constant, and this is what looks like ellipses or ellipsoids in d dimensions. Okay, so what are the contour lines? We need to take an eigendecomposition of the covariance matrix. By the spectral theorem, that eigendecomposition is going to give us two vectors that are orthogonal, and this is the variance parameters in each of those dimensions, the standard deviations that tell us how stretched the densities in each direction. Okay, so in this case, you see that the axes are basically these diagonal vectors, and again, the eigenvalues are going to tell us how stretched out the density is in each of those directions. In this case, lambda 1 and lambda 2 correspond to the square of the standard deviation parameters. This is why the actual stretch is equal to square root of lambda 1 and square root of lambda 2. That's the sigma 1 and sigma 2 parameters. Okay, this is just to show you that they're completely encoded within the covariance matrix parameter. That's the parameter that we need to estimate from data. We only need to estimate the covariance matrix parameter and the mean parameter that tells us where the density is centered. How do we do that? How do we estimate those two parameters? We apply log likelihood. What does the log likelihood of the Gaussian parameters look like? It's just the log of, under IID assumptions, of course. Remember that when we're applying the likelihood, we're essentially modeling each data point as, when we have IID assumptions, as an independent random variable that has the same joint distribution of its variables in this case. Okay, that's what I mean by joint distribution. That's where the identically distributed part comes in. So here we have n data points, which are d-dimensional. And again, we assume that each of the n data points, they're independent, they're mutually independent, but within their d dimensions, they have this Gaussian joint PDF. So we write it now, and now we interpret this as a function of mu and sigma that we want to maximize to find the best mu and sigma that adapt to the data. This is more difficult than what we did in the case of the simple Gaussian in 1D or the exponential in 1D, because we have to fit many parameters at the same time. But let me show you how it's done. So this, when we apply the log, we obtain this formula. And now we're maximizing, but we have a minus. So basically we minimize. And you can see that this is some kind of weighted least squares problem with respect to mu. And it's a more complicated function with respect to sigma. So now what we should do is, this is a bit of multivariate calculus. It's not too important for the rest of the course, but I just want you to know what you would do here is you would check whether the function is, when we're minimizing convex or whether we're maximizing concave. So let's imagine that we're still maximizing. We want to know if it's like a inverted bowl like that, so that when we take the gradient and we set it to 0, we know that we're on top of the bowl. How do we know that we have a bowl like that? The Hessian needs to be negative semi-definite or negative definite, even better, so that there's a single maximum. Probably you have heard this, you might have heard this in the context of minimization. There you want the bowl to look like that. This means that the function is convex. That means that the Hessian is positive definite. If that happens, then you can set the gradient to 0. So in the case of mu, this is going to be relatively straightforward. In the case of sigma, this covariance matrix parameter, it's very complicated. So I'm not going to do it here. You can go check out basically any textbook on Gaussian random vectors to see the derivation. It gets pretty complicated. And it's not super interesting. So let's see what we would do for the mean parameter. I'm only going to derive the gradient, not the Hessian. So the gradient is just equal to this inverse sigma times xi minus mu, and this guy is positive definite because we know that the eigenvalues are positive, right? So then the only way that quantity can be 0 is if this is 0. So this tells us that actually the mu parameter is just, or can be obtained by averaging each entry of the data points. Okay, these are d-dimensional vectors. We sum them up. That's like summing them up entry-wise, and then we divide by the number of data points. So that makes a lot of sense. The mu parameter where things are centered is just obtained by averaging the data points. Again, you would still need to check that the Hessian with respect to this parameter is positive definite. So you have found this minimum of the minus log likelihood. We're not going to get into those details. You can believe me that that's the maximum likelihood estimate. For the sigma parameter, the covariance parameter, it gets even more complicated. We're not going to do it here. But interestingly, once you figure out that indeed the Hessian is positive definite and you can set the gradient to 0, what you obtain is something that is very close to the sample covariance matrix of the data, which is very satisfying because if you remember, for us, when we have a single Gaussian random variable, the maximum likelihood estimate is equal to the sample mean and the sample variance. We haven't talked about sample variance yet, or the sample standard deviation. Here we get a direct generalization. The mean parameter is equal to the mean of each of the entries, or equivalently to the vector mean of the data. And the covariance matrix parameter is just something that is very, very close to the sample covariance matrix of the data. Again, we haven't talked about covariance matrices yet. We'll get back to this when we do. All right, so let's take a look at our data again. Here we're in very low dimensions, so we can actually compare what the Gaussian model does compared to multidimensional kernel density estimation. This is what we observe for multidimensional kernel density estimation, and this is the Gaussian model. They're very close. It doesn't look like we're losing anything here from the parametric model. In higher dimensions, this guy would be completely impossible under conditional independence, unless you have conditional independence or independence assumptions. This guy we can still compute by just computing the covariance matrix and the mean. Of course, you are going to miss a little bit of structure. We can see this when we do the same thing for height and weight. Here, from the joint density, you see that the relationship is not as linear. So, we see like a tilt upwards here, where, let me get this right, these people are heavier than maybe they should be, and these people are less heavy than they should be. So the taller people tend to be a bit thinner than you would expect if things were completely ellipsoidal. And the Gaussian density is not able to adapt to that. That is the price to pay for having a smaller number of parameters, but that price to pay, we have to pay it anyways when we go to higher dimensions, because this is actually impossible to estimate in general. You have to make independence or conditional independence assumptions. All right, so what have we learned? We have learned the definition of Gaussian random vectors, and in particular that they have an intuitive interpretation in terms of the contour surface that are ellipsoidal, and we want them to adapt to the data. So that motivates introducing this covariance matrix parameter that generalizes the definition of the distribution. Then we have shown how to estimate using maximum likelihood estimation, and we showed a couple of examples with real data to illustrate that it makes sense. And that's all I got. Thank you very much.